Hello everyone and welcome to Signals, Systems and Signal Processing with Wolfram U. This lesson is on system properties. We will start by defining what we mean by a system in general, and then go over a few examples of systems in continuous time and discrete time. We will then study system properties. We will discuss memoryless systems, stability of systems, and other important properties such as causality, time invariance, and linearity. Systems are defined as a transformation of the input signal to the output signal. You can think of a system as a black box that takes the input signal x of t and returns the output signal y of t. In discrete time, it will be the same. The input and output signals will be x of n and y of n. For the first example of a system, consider a simple series RC circuit. It consists of a voltage source, a resistor R, and capacitor C, which are connected in series in a single loop. If we call the voltage across the input source x of t and the voltage across the capacitor y of t and apply the Kirchhoff's voltage law to this circuit, we get a first-order differential equation as indicated here. This way, we have mathematically modeled the RC circuit, and now to find the output signal y of t, we can simply solve this differential equation given x of t and this RC parameter. A moving average system is another example of a system, this time in discrete time. It averages over n consecutive input sample values as shown here. The output at any given time is the average of n values x of n together with some delayed versions of x of n. Let's look at this example. On the right-hand side, we have a picture of Fourier, a French mathematician and physician. He invented an elegant concept called Fourier series, which makes the basis of this course. It is the foundation of the Fourier transform that we will discuss later in great detail. The data shown on the left-hand side is taken from a row of the same image. Applying moving average or mean over the past n entries for different values of n, you can see that by taking the average, the data is getting smoother. Same for the image. When n is larger, the average is taken over a larger time frame. We use moving average whenever we want to smooth the data and reduce the signal noise. For the next example, let's look at the exponentially weighted moving average system, which is very similar to the moving average system with more emphasis on data samples near the time instant n. Let's see how this is done. The exponentially weighted moving average system is defined by the equation indicated here. This equation gives y of n in terms of y of n minus 1 and x of n, and alpha is a positive number smaller than 1. If we use the same difference equation to write the y of n minus 1 in terms of y of n minus 2, we get this new equation. Going one more step to y n minus 3 and simplifying, we get the equation shown here. The weights or the coefficients of the older samples, the more delayed samples, decay exponentially. Remember, alpha is less than 1. Because of this, we call this system exponentially weighted moving average. The older samples are less important. They have less weight in the average. I say older samples, this could be farther samples if the independent variable n represents the spatial, horizontal, and vertical positions of the pixels in an image, for example, instead of time. Applying the transformation again, and the same sample data and the entire image for different values of alpha this time, you can see that here we are putting more emphasis when smoothing the data on samples which are closer to the time instant n or position n for the image. To make it easier to study systems, we define certain properties for systems and then turn our focus to a class of systems which have a certain property. The first property that we define for systems is memoryless. When the output at any given time, let's say t0, only depends on the input at the same time, t0, we call the system memoryless. This definition applies to both continuous time and discrete time, at any given time t0 or n0. As an example, for a system where y of t is equal to a times x of t, the system is memoryless since the value of y of t only depends on the value of x at the same time t. As another example, if the system is defined with y of t returned as t minus 1 times x of t, again, knowing the value of x at time t, we can find the value of y for the time t, and so the system is memoryless. Here are a couple of more examples where the system is not memoryless, and we say it has memory. The first one, y of n is equal to x of n minus 1. The system is not memoryless since to find the value of y at n, we need to know the value of x at n minus 1. This system is called unit delay. The output is a delayed version of the input, and delays, in fact, require memory. The next example where the system is an integrator also needs the past history of the input over a period of time in order to be able to take the integral. This again requires memory, and so the integrator is not memoryless. The next property to discuss is stability. For this one, let's start first by the definition of bounded signals. We call a signal x of t bounded if there exists a real number a such that absolute value of x of t is less than a for all time t in interval t, which is the interval over which x of t is defined. With this definition, we say a system is stable if and only if for every bounded input, the output is bounded. We call this type of stability bounded input, bounded output. So the whole idea here is that if the input stays below some finite value, then with a stable system, the output will also stay within some bounds. Let's look at this system, which returns y of t as t times x of t. Now, if we consider the bounded input x of t defined as shown here, the output will be y of t equals to t times sine of t for values of t that are greater than or equal to 0, which is unbounded, and therefore the system is unstable. This can also be seen in the plot of the signal. X of t is bounded and y of t goes to infinity as t goes to infinity. The next property is causality. A causal system, both in continuous time and discrete time, is defined as a system whose output at any given time t0 depends only on the input at that time t0 and before that. This means that if the past history of x of t is 0, for example, for t less than 0, the output should also be 0 for t less than 0. These can be then examples of causal system responses, whereas these responses are non-causal system responses. X of t is 0 before time 0, but y of t is non-zero for t less than 0. For this example, let's look at a series of input-output signals and decide whether the system is causal or non-causal. Assume we have a system that for this unit square input signal returns the unit triangle output signal. Is the system causal? Yes, the system is causal because the output does not precede the input in time. However, if the input-output signals are as shown here, the system is non-causal since the output precedes the input in time. If you look closely, you can see that the input for t less than -1 is 0, but the output is non-zero. Time invariance is another property we define for systems. First, note that we sometimes use this notation here with the arrow to denote the input-output signals of the system. For a time-invariant system with input-output signals x of t and y of t, if the input is shifted in time to x of t minus tau, then the output will be y of t minus tau, that is, y of t shifted in the same way. It is as if the system does not see or care about the location of the origin of time. If you shift the input signal in time, the output will also be shifted in the same way. We call this system a time-invariant system. Let's say for a system, this unit square input signal gives the output signal as shown in this plot. We want to know if the system can be called time-invariant if the input in this second plot gives the output shown. This system is time-invariant because in the second plot, the same input is shifted by 1/2 and the output is also shifted by 1/2. If this was the input-output of the same system, then the system would not have been time-invariant. X of t is shifted here to the right by 1 unit of time, and the output is shifted to the left by 1. Therefore, this system is not time-invariant. Another property which a system may or may not have is linearity. Given input-output signals x1 of t and y1 of t and x2 of t and y2 of t, if we have a new input signal x of t, which is a linear combination of x1 of t and x2 of t as indicated here, A system is said to be linear if y of t will be returned as the same linear combination of y1 of t and y2 of t. As an example, let's see if the system for which the output y of t is x of t squared is linear or not. If we test this system by the input x of t, a linear combination of two input signals, x1 and x2, the output will be x of t squared. Expanding this expression, you can see that this is not equal to the same linear combination of y1 and y2, and so the system is not linear. Let's look at another example. Assume y of t is given as x of t cosine of omega 0 t as shown here. We want to find out if this system is linear or not. Again, we can test the system by using an input signal x of t, which is a linear combination of x1 and x2, replacing x of t with this signal and simplifying the results. You can see that the output is also the same linear combination of y1 and y2, the output signals to x1 and x2. And so this system is linear. Finally, we call a system LTI when it is both time-invariant and linear. Linear time-invariant systems are an important class of systems. They will be the focus of this course as the course develops. For the last example of this lesson, consider an LTI system where the unit square input, as shown here on the left-hand side, gives the unit triangle signal on the right-hand side. The question is, knowing that the system is LTI, can we find the output of this new signal, WT? If we think of WT as a summation of these signals, which are shifted and scaled versions of the unit square input, this means that WT can be written as the summation given here. Then since the system is linear, we can write the output as the summation of the output of these signals. And the output of these signals, for example, x of t minus 1, will be the shifted version of y of t by the same amount, y of t minus 1, since the system is time invariant also. So the output of WT, if we call that ZT, for example, can be simply written as shown here. This graph also shows the input-output signals omega t and ZT together. To summarize, in this lesson, we defined systems and we went over a few examples of systems in continuous time and discrete time. And then we learned about different properties of systems, namely linearity, time invariance, causality, stability, and memoryless.